Okay, I think it's working. All right, so the rate of change these are the words you're writing down. In temperature, actually, can I see your notes for a minute, Andy? I want to see if there's anything that you already have up here. Sort of. Look at the very first statement there, where it says according to Newton's law of cooling. Okay, we're going to do a slight translation into calculus. Do we know rate of change is that derivative? Okay, in temperature, and you can edit on your notes or you can write it down again. Of an object. In this case, it's dead bodies. Like, if Tristan keeps talking, he's going to be the dead body in the problem. Is proportional. Do you know what proportional means? We'll get to that. To the difference, and this is the difference. It's a difference. It's not proportional directly to something. It's different to a difference. Oh, I wrote difference. Between the object's temperature and the surrounding temperature. Can I abbreviate temperature TEMP? I'm going to anyway. Now that surrounding temperature, that's called the ambient temperature, often. So if they say ambient temperature, that's what that means. Okay, let's define some variables for you. T naught, the little zero. That's the initial object temperature. And generally our problems, well, it can be, and this is with time. Actually, that's at time zero. We'll get to units in a minute, because it could be Celsius or Fahrenheit or Kelvin or Rankine. I don't know what it's going to be. Could be any of it. I'm speaking of the AP test. It can be any of them. It's just a temperature scale. All right, then there's T sub little a. That's the ambient temperature. Like the air. And in the dead body problem, in one of the, I remember I was a kid growing up watching one of the mystery, daily or weekly shows. They got the time of death of the body wrong because the body had been hidden in a wine cellar. And the outside temperature was much warmer, and so they had it all wrong. They had it much earlier than it actually was. So ambient temperature, that's the surrounding air. Sometimes it's water. Sometimes it's oil. If we boil Tristan in oil, something like that, right? Yeah. So whatever it is. And then there's just T. We'll say this is with respect to time. And this is just the temperature of the object, how it changes with time. So what happens to Tristan's body temperature with time after we decide he's going to be our dead body? Okay, and by the way, this is really, 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 really oversimplified. It really doesn't work at extremes. It's assuming constant ambient temperature and a constant rate of change and no environmental impact. So this is like the rule of thumb. This is like a real quick check. The guy goes out in the field, tells the detective that the time of death was around between this and this. They just did Newton's law of cooling real fast. Something like that. It's a rule of thumb kind of thing. In reality, they go back, and if they want to get a better time of death, they have to put in what was the temperature outside if the body was outside the whole time? Was there rain? Was there any precipitation? Was there any other mitigating environmental factors? But it's a good first cut. It works real well for things that are very well controlled, like an oven, and we're talking about a turkey. That works. It works real well on turkeys. Okay, so what does those words mean? You have to translate these words. See that is? That's an equal sign. It's been an equal sign since you were in Algebra 1. Still an equal sign. So rate of change. What's rate of change in calculus? But this is rate of change in temperature. So would that be d capital T with respect to d little t? Change in temperature with change in time. Would that be a rate of change? Yeah. That's the rate of change. Difference. What's a difference? It means minus. We're going to subtract. So when we talk about the difference between the object's temperature, that's T, right? That's the object. And generally, that's supposed to be initial. No, it's, yeah, anyway, it can be T or T naught, and then surrounding temperature is always T sub A, and it's assumed to be constant. It's assumed. Okay, so how do we write this out? So we're going to take that, and we're going to go, okay, the rate of change, that's dt over d little t, is equal to, is, right, proportional. Remember proportionality constants are K? Everybody uses K. It's very confusing. So when I was a hydrogeologist, they used permeability. They had a K, but it was different than the engineering permeability, which was also K. They had different units. They were referring to different things. And it was very confusing because they used the same word and the same variable, but it was different. So you have to be careful about that. But it's proportionality constant. We use it for all kinds of things. And then it's the difference. So it's the object's temperature minus, because when you say the difference between the object's temperature and the surrounding temperature, that means capital T minus T sub A. Is that a differential equation? Is it a derivative? Is it an equation that has some relationship? Then it is a differential equation. That's why it's in this unit. So the first step is always to take the words and translate them into a differential equation. Hence why I have to do it for homework, because I'm taking differential equations. When they say solve this problem, they mean solve the differential equations. Does that mean I need to separate variables and integrate? So what's our second step? Our second step is to separate and integrate, right? We're going to separate, variables and integrate. So, do I need to get the t's on the side with a capital T? So I have integral of 1 over t minus t sub a dt is equal to the integral of k dt. That proportionality constant. It's a constant. It's just a number. So does that just mean I'm integrating that with respect to little t? Right? Okay, we know how to do this. Does this look like natural log? Is that 1 over u? Remember, t of a is a number. It's constant. So is the only variable t, and what's the derivative of capital T? It's d capital T, right? So is this just going to be a natural log? Step 3, is this going to be natural log absolute value of t minus t sub a is equal to, what's the integral of k dt? kt plus c. And we'll call this C1. Because like last week when I started giving you the hints on where we were going with this, did we have more than one C by the time we were finished? It was still, because how do we undo? We got to get the t by itself. How do we undo natural log? I am numbering these steps. You should too, because guess what's going to happen? I'm going to give you this statement or something very similar to it. I'm not going to define the variables. I'm going to say write the differential equation and solve it. Do I need to see all these steps? Am I telling you what I want to see? I am. I'm kind of giving it away. This will be a question on your test. Because this is the calculus. The rest of this is not so calculus, but this is the calculus. Okay, how do we undo a natural log? So we have e of natural log of t minus t sub a equals, bless you, allergic to Newton's law of cooling, huh? Okay, from last week, what happens when you have a same base but you have the sum of the powers? How can I break that up?
Multiply.
Yeah, so it's e to the kt times e to the c1, but that's just a constant. We're going to call it c. Well, does this e undo the natural log? They're inverses, so I get T minus T sub A, which is ambient temperature, is equal to C e to the KT. Looking familiar yet? I need to see this step. All right, so we're not quite done yet. I want T by itself. Do I solve for T? The object's temperature is equal to the ambient temperature plus C e to the KT. But I'm not happy with that. Just finding C is not enough. I mean, not finding T is just, I need to get rid of the C. To truly solve a differential equation, if you have enough information, you should solve for C, and we're about to do that. So do we all agree that when it first starts out, that the temperature is equal to T sub naught? It's there's some initial temperature, right? So step 7, time at 0 is equal to T naught, which is equal to T sub A C e to the KT. Or I could go back to this form right here, and I could say, oh, it's T naught minus T sub A equals C e to the KT. I am now going to solve for C. What do I have to divide by? E to the KT. I'm going to the next page. Can I go to the next page yet? Oh, wait, I forgot something. T is 0. It's 0. Oh, does this thing go to 1? Do I know what C is? Right? And I'm about to plug that in. There we see how I got my C. Yeah? So that's the 8th thing. This is the 8th step. I need to see, you need to tell me that C is equal to T naught minus TA. And my final step, ready? Everybody ready? No, y'all aren't screaming.
Wait, hold on. Did you forget a plus sign?
Where?
Step 7.
Yeah,
Okay, now moving right along, what's my final step? T is equal to T sub A plus my C, but my C is T naught minus T sub A e to the KT. And you should have learned to just use that equation when you were in pre-cal. Can I borrow your examples again, Andy? Let me make sure that I got the same examples. Oh, I gave a different example. Oh no, I just said it was a turkey. Was it? Okay. It's okay. Everybody look at example 2. You have a heating plate. I called it a turkey, but that's okay. So, example 2. On example 2, reading through your problem, what is your initial temperature of your heating plate? 180 degrees. Do they tell you what kind? Fahrenheit? Do they tell you Fahrenheit?
just degrees.
Okay, it's Fahrenheit. If it's 180 degrees, it's Fahrenheit. Do they tell you an ambient temperature of the air?
60.
60 degrees Fahrenheit. Go ahead and put Fahrenheit. What else do they tell you? In a third of an hour. Did they tell you in a third of an hour?
Yeah.
Uh-huh. 20 minutes? Did they say 20 minutes? Well, it's 20 minutes. Does that equal 1/3 of an hour? Okay. At 1/3 of an hour, what was the temperature? Did they tell you?
150.
150. And in part A, what did they ask for?
What's the temperature at the end of 1 hour?
So the reason I knew to change to hours is because they asked me for the temperature at the end of 1 hour. Before I can find the temperature at 1 hour, do I need to find an equation? Do I need to find everything? So what am I missing? I'm mainly missing K. Okay? All right, so let's go through this. I'm going to show you the calculus again. So if you're doing one of these problems and you remember the formula, can you write it down and just use it? If nothing is required where you have to, don't worry, there's enough math in here that I'm happy. But I'm going to, no, we're not going to derive the equation. We just did it. Okay, so we're going to use the equation we just got. We'll derive it again another day. So do we all agree that it's the ambient temperature? What's the ambient temperature? 60. And is it plus C, which is the initial temperature, minus the ambient temperature? All times e to the kt. Agreed? Right? Can I use this 1/3 hour to find K? I'm going to. I know that in a third of an hour, the temperature is 150 degrees. That's going to be, 60 plus 120 times e to the k over 3, because it's 1/3, right? Subtract 60. What's 150 minus 60? Huh?
90.
Yes, I didn't hear it. 90, and I'm going to divide by the 120. Can I do that all in one step, or do I need to show you the steps? Okay, I subtracted 60. I don't care. Oops. 120 e to the k over 3. That means it's going to be 90 over 120 equals e to the k over 3. I can't write today. Okay, 90 over 120 is 3/4, right? I need to undo an e, so I'm going to do a natural log. Natural log, natural log, natural log, and I'm going to put this stuff in there. This is e to the k over 3. This is 3/4. So when I do that, do I get, this undoes, so do I k over 3 equals natural log of 3/4. Multiply by 3, does k equal 3 natural log of 3/4? Agreed? You could put this in the calculator, but I'm going to warn you now. If you get a Newton's law of cooling problem on the AP test, that's an easy problem. You're going to screw it up by rounding wrong, because it's going to be on the calculator section. Do not find k and round to 3 decimals yet. You don't round till 3 decimals till the very end. If you don't carry it along, is this the exact value of k? There's an approximate, but we don't want that. You don't want a rounding error. And I guarantee you on these Newton law of cooling problems and the exponential growth and decay problems, if they make you find that proportionality constant, it will be wrong if you round here. So I need you to practice getting the exact. I'm going to look for this. Okay? You're going to get me the exact, even if I give you a calculator. Okay, that's my K. Now do I have the exact equation? My temperature of my heating plate is going to be 60 plus 120 e to the 3 natural log of 3/4 every single time. Another way, and then t. So if they want to know in 1 hour, do I just put in 1 hour for the T? Right there. They want to know what the temperature is in 1 hour, correct? So I'm just going to put in a 1 there. So temperature in 1 hour is equal to 60 plus 120 e to the 3 natural log of 3/4. And I want to show you a trick. 60 plus 120. I know that I can simplify this by moving that as a power, and then they will undo each other because I have e natural log of 3/4 raised to the 3 power. Those undo each other, and I get 60 plus 120 times 3/4 cubed. Isn't that fun? It is. It's kind of cool. And I can simplify it more, but that's for another day. All right. That wasn't too bad, right? And if you had a calculator, would you round to 3 decimals? Okay, what's the next part? What do they ask for? That was part A. What do they ask for in part B?
When will the temperature be 100 degrees?
Okay, that means 100 equals 60 plus 120 e to the 3 natural log of 3/4 t. Yes, and they want that t. Is this just like finding k? Same math. Subtract 60, you get 40. Divide by the 120. 40 over 120 is 1/3. That equals e to the 3 natural log of 3/4 t. How do I undo an exponential? Natural log, so I'm going to take the natural log of the whole thing. That's natural log of 1/3 equals 3 natural log of 3/4 t. Divide by this. So you're going to end up with t is equal to the natural log of 1/3 divided by 3 natural log of 3/4. You're going to round that to 3 decimals, and that's approximately 1.273 hours. And we'll save the other one for another day. I need y'all to practice, because you're going to have to do, even on a calculator section, I expect to see how you did it, not just 3 decimals.